Hello, welcome back. We need to pick up from where we left off, which is, the regression of uh, the index model, single index model. In other words, regressing, uh, excess return of a particular stock or company over S&P, the broad market portfolio represented by S&P 500. So we found, correlation matrix, covariance matrix and correlation matrix last time. And you might wonder, here, because we got correlation matrix by, in a single shot by using, data analysis. And in data analysis menu, you could have also might have seen, covariance matrix as well. But again, I don't recommend that because the covariance matrix in data analysis is by default only the population covariance matrix, population covariance. So it's not sample covariance. So it's going to be, a completely different number. Okay. So now let's think about, regressing to find beta. And also it gives you an alpha because it's excess return. We're regressing excess return over excess return. So the result, if there is any vertical intercept, that is the alpha that we are seeking. Actually, alpha is the one of the most coveted, one of the most sought after characteristics of any asset or portfolio, because alpha means there is the return is already the return on the asset or the portfolio is already saddled like riding on a saddle. It's saddled over like horseback. You have already additional built-in saddle in whatever you're riding, right? So there was a famous movie called Hunt for Red October in late 1980s, starring Sean Connery, playing the role of some old Soviet era submarine admiral, and who was trying to defect to the West with this submarine called Red October, supposedly a nuclear submarine. And that movie was 1980 something, 87, 89. But after that movie, there was also a famous paper titled Hunt for Alpha. Hunt for Alpha. And what is that about? Well, it's obvious, it's clear. Everyone is seeking alpha. We want, and whatever, even with the same beta, if alpha is positive, whereas beta is given two stocks or two portfolios with the same beta, but which one would you prefer? A portfolio or stock with a positive alpha, or with zero alpha, or negative alpha? Of course, nobody will choose zero alpha or negative alpha over positive alpha, right? It always gives you an abnormal return. And as I said, abnormal in this case, in this context, as a positive thing. It's not abnormal, like uh, not a negative connotation, right? Um, I mean, if you someone says he's abnormal, it's usually bad, right? Isn't that right? Um, uh, but if it means he's abnormally good looking, oh, why wouldn't that's a compliment? That's a very good. It's like saying extraordinary can be used both positively or negatively, right? I mean, he's extraordinary, and usually it has a positive connotation. But what if his his extraordinarily dumb? Right? Um, but in our context, abnormal is always positive and means you're getting abnormally high return. In other words, over and above what is being predicted by uh, you know beta and the uh, market risk premium, right? Which is systematic. Um, so we want to do to run regression. What we need to do is since we already there are two ways we can do that. There's but uh, basically you know what beta is, and I've been telling you beta is um, let me insert. I've been telling you over and over. I've made this distinction between this. I, I would just what's going on? I would rather switch to a okay, and back to PowerPoint, and you should be able to see just about now. Yeah. So beta is basically and we talked about this already in previous um, on many previous sessions. It's also a correlation coefficient, but beta is a correlation running just one way. If correlation runs one way, I mean, isn't that causation? Causality, isn't it causality? But they always say, they don't say it is, causality, it's just correlation. But look, when one thing is dependent variable and the other thing is independent variable affects whatever is happening in the dependent variable. And in that case, correlation, isn't that just one way? Because it always runs from x to y. And then it is causation. I mean, no matter what they say, I believe, because if correlation runs only one way, what can it be? X causes y, right? Whatever happens in X causes whatever happens in Y. But anyway, the formula is, this is the formula, covariance between X and Y, covariance of X. And I've been, comparing, both beta and rho. Rho is also a correlation coefficient, but in case of rho, the correlation runs both ways. Neither of them are independent, right? They are not dependent, independent variables, right? They are both, independent variables, right? So the difference, I've been telling you, beta between X and Y up to the numerator. Oh yeah. The numerator is the same thing. It's the covariance between x and y. But the denominator is variance of x. Variance of x squared. In other words, the variance of independent variable. Okay, so that's the difference between the two. So we can find beta this way as well. But then, regression would be and that this process of finding, this beta value, right, which is the slope of the line, the slope of the correlation between, x and y. So this is basically, regression, but what I'm talking about is, pre-built program, right? So let me switch back to Excel. I should be seeing it just about now. So to run regression, and I'm gonna, will there be enough space there? Not sure, so I'll have to bring it down here. So in our last class, I showed you how to invoke the data analysis package that is, that automatically comes with Excel, but most of the times, people, not everyone using Excel is a, using, data analysis. I mean, they don't even know. Accounting just, it's plus minus, right? It's addition, subtraction, at most, on a very low elementary level, intro level accounting, it's just, subtraction, division, addition, division, subtraction, multiplication. So not too many people know about the data analysis, but I showed you how to turn it on. So in your, data ribbon, right? This is called ribbon. You have to click on data analysis, and then it's in alphabetical order. So scroll down until you find regression. Okay, you see that regression. And then of course hit OK. What else? And then you enter data. Input Y range. Y is individual stocks excess return. So I highlight, right, this range. Don't forget, you don't enter average, right? Average is, not the part of the primary data, original. And you can include, labels, because it will come in handy later. And then, what is the, Y is the dependent variable, right? And X is the independent variable. And what is the independent variable? S&P 500, right? Oops, and I click on this. Listen, why? Because always, this is Finance 100, Finance 100 concept, right? You cannot have individual stock affect the entire market. The entire market will always affect individual stocks, as long as there is some correlation, unless their correlation is zero. But think about it. That is the case when market moves up market goes up, that means, all the stocks are being pulled up, most of them. If there are stocks with negative correlations, they will go down. But, when market is, rallying, most individual stocks are positively affected. The market goes down, individual stocks also, go down. They get affected. So that means, market is the independent variable. Individual stocks are dependent variable. So I do that, and I let them know. Let it know. Let Excel know. I don't know if Excel is a guy or girl. Of course, it's it. Some languages, we call it her. Romance languages, French, Italian, and Spanish, with grammatical genders, right? I guess Excel is masculine, not feminine, because it doesn't end with E or A or. Now, our confidence level, we give 95% confidence level. And output range, we select one cell, and it's going to automatically. I will select A22 for output range. We're done. All you need to do is, simply hit OK. And there you go. We have summary output. Summary output is, necessarily the highlighted areas, and we had 2 more rows, but I would like to actually give it some outside border and give it nice font so that it would be more appealing to the eye. So what does this tell you? First thing you see is R square. R square, I'm going to highlight this. And I'm going to come back to that later. Take a look at the coefficient. Coefficient means what? That's beta and alpha. Intercept, that's alpha. So S&P 500 is X. So X's coefficient is beta, right? And the intercept is alpha. It's got alpha, ABC's got a very good, ABC, very good alpha. So and then next thing you want to see is t-statistics. Why? What does T mean? What does t-statistics mean? T-statistics is a metric, right, that would tell you if this estimate, right, coefficient estimates of the coefficients are robust, right? Not by chance, or not by fluke, right? It's not a happenstance. This is going to be. This is a robust observation, a robust estimate. And how do I know if it is robust? If this number is greater than 2, it is clearly robust. Okay, this one, so beta is not greater than 2, but just about close. 1.83 is close. So this is not frivolous. This is not a frivolous estimate. Okay, or superfluous. This is not a frivolous estimate. As opposed to that, the intercept, although this is 4, this may not the chances of this 4 being, significantly different from the 0 is very low. That's what it means. Significantly different from, so it won't be significantly different from 0. In other words, um, this is a happenstance. This is by pure chance. This intercept, this estimate of intercept, vertical intercept, came out to be 4.3. Its probability is actually low. I mean, it's not a robust, estimate. Meaning, the chances of this estimate with just one, we ran one regression, but if I run this regression is based on what? Let's past 10-year data, let's say. If I use, another 10-year time frame, not the most recent 10 years, but second most recent 10 years, right? The third most recent 10 years, right? Second most recent 10 years is like, 20 years ago to 10 years ago. Third most, recent 30 years ago to 20 years ago. But if I keep using between, 15 year last, P minus 15 to P minus 5. Understand? A 10-year time frame between 15 years ago and 5 years ago. If I use, this 10-year time frame replicated over and over, will I still get something like this? Yeah, that means, it's not likely you will get consistently, right? But, this means, and if it is like 2, will I get an estimate? Will I get a coefficient, data coefficient like this? And if it is close to 2, the answer is yes. You will get, consistently. So that's what is meant by robust estimation. Okay. And the also p-value. P means probability, and yours might wonder, well, if p-value is like, probability is like, it's like 10%, isn't it very low probability? Yes, but what it means is the probability of this estimate being no different than 0 is this low. That's what it means. And this probability is like almost 80%. What that means is the probability of this estimate being different from being not different from 0, right? Is almost 80%. So there's an 80% probability that this estimate, if you run other regressions over and over with a slightly different sample, the vertical intercept alpha value will most likely 80%. There's an 80% probability that the alpha value will be no different than 0, right? So that's what it means, right? And the rationale behind it, and I said, if p value is 2 or greater than 2 means, robust estimation, right? And why? And that means, there's, the chances that this estimate is not by chance or by fluke or by happenstance, that such a probability is very low. But think about it. Low probability means, what? Remember, in normal distribution, right? Low probability means extreme tail end, right? Low probability means extreme tail end. And the extreme tail end has, what is extreme tail end? What is the standard deviation that defines the extreme tail end? Standard deviation is 2, right? Extreme tail end is outside 2 standard deviation. And if any data point is lying in this area, upper tail, lower tail area, which has only like 2% probability, respectively, right? Each, right? And in a standard normal distribution, what is the mean? In the standard normal distribution, the mean is always 0, right? And standard deviation is 1. A standard normal distribution, right? Mean is 0, right? So what and I said, what t-statistics is telling you is that if this t-stat is, 2 or greater, then the chances of this estimate being, no different than, 0 is very low. In other words, this is an estimate that has, like 2% ability of happening. In other words, the mean of this estimate is not 0, right? If you're, running regression over and over, with slightly varied sample data, and this is, related to hypothesis testing, and if you have taken statistics, you might remember what hypothesis testing is. Hypothesis testing is, basically, you have an observation, and in the observation, you have 2 hypotheses. One is, called, null hypothesis, and null hypothesis is H null or H1, and alternate hypothesis is HA or H1, and in null hypothesis, the mean of our estimate is 0. And the alternate hypothesis, the mean is non-zero, right? So if t-statistics is, like, higher value, 2 or higher, and means, this null hypothesis is rejected, okay? Meaning, this is all statistics. Because So probability of this estimate happening is, in this range, right? Outside two standard deviation range. So it's not a frivolous estimate, right? I mean, if it is within like closer, if t-value is low, that means it's, that estimate has high probability of being uh, not beating this mean, right? That's what is that's what it is, based on, right? The hypothesis testing, and this alternate hypothesis is accepted, right? Uh, the mean is non-zero, right? In other words, or uh, true mean would be significantly different from zero. So these are the numbers that you have to look. And also, oops, earlier, I said you have to look at the R square as well. And this R square is kind of frivolous. I mean, low, not frivolous. But it's natural. I mean, R square represents what? Goodness of fit. And if the goodness of fit is 1, then I say there's no error, there's no alpha, right? Everything falls exactly. I mean, everything is explained, by all, returns are explained by beta times, market return. And then everything will fall on, exactly on the regression line. That's, that's not normal. I mean, that is, artificial, very artificial. From, how can, think about it, how can ABC and S&P have, perfect, fit? NBC and ABC will have perfect, correlation, perfect, right? Or goodness of fit will be 1, but uh, that's not the case. Now, we want to do also XYZ and S&P 500. We're out of time, but it doesn't take that much time now that we know how to do it. So let me. I want you to also do this, as well. So go to our data analysis, select regression. This time our y is XYZ. Also X is still S&P 500, right? No matter what, it's always as market is always the independent variable. So, and we're gonna plot it where? We're gonna 22. Okay, and we got it. All righty. So let's see. It doesn't have to be that wide. Now, let's compare. The R square is even lower, right? And then, alpha is, something like 1 point. What's important is the t-stat, and the beta is beta is 0.59, and its t-stat is not that significant. If it is not significant, I don't even have to. Just for, because that's an estimate. T-stat is, not significant, right? So not a robust estimate. R-square even lower. Okay, so this is basically, regression of, a single index model. We found, beta and alpha, but only, ABC has sort of significant beta estimate, and XYZ doesn't. And so the time is up. I'll have to stop the video, and I will stop recording and see you guys in the next video, next session.